let us discuss the instrumentation of UV spectroscopy. A single beam spectrophotometer. A single beam spectrophotometer is a device that measures a substance light absorption using one light beam to determine its concentration, purity, and chemical characteristics. Single beam spectrophotometers cover the UV to visible wavelength range and offer highly reliable measurements. It sequentially measures the intensity of the light after it passes through the sample and the reference, usually empty. Single beam spectrophotometers cover the UV to visible wavelength range and offer highly reliable measurements. Spectrophotometer is an instrument designed to measure the spectrum of a compound. Instrument used to measure the absorption in UV, the range between 200 and 400 nanometer, and visible 400 and 800 nanometer region is called as UV visible spectrophotometer. A spectrophotometer records the degree of absorption by a sample at different wavelengths, and the resulting plot of absorption versus wavelength is known as spectra. UV instrumentation, specifically UV-vis spectrophotometry, measures how much UV and visible light is absorbed by the sample, allowing for the quantification and identification of compounds. The basic components of a UV-vis spectrophotometer include a light source, a monochromator or wavelength selector, a sample folder, and a detector. These instruments are widely used in various fields like chemistry, biochemistry, and the environmental science. Thus, UV spectroscopy works by measuring how much ultraviolet and visible light of a substance absorbs. This absorption is linked to the substance chemical structure, allowing for identification and quantification. The process involves a spectrophotometer that directs light through a sample and measures the intensity of light that is transmitted, providing information about the sample's absorptions at different wavelengths. A UV-vis spectrophotometer consists of a light source, monochromator, a detector, and a data recorder. The light source provides illumination at one or more specific wavelengths. The monochromator is used to select the wavelength of light that passes through the sample. Principle of UV-vis spectrophotometer. UV-vis spectrophotometry relies on the interaction of light, ultraviolet, and visible light with matter, enabling the identification and characterization of molecules based on their absorption patterns. The principle involves passing a beam of light through a sample and measuring the amount of light transmitted at different wavelengths, which is directly related to the concentration and properties of the absorbing substance in the sample. UV-vis spectrophotometers are used to analyze the absorptions or transmission of light through a sample across the ultraviolet and visible regions of the electromagnetic spectrum. They are used for both qualitative and quantitative analysis, enabling the identification and quantification of substances in various samples. The components of UV visible spectrophotometer: light source, filters and monochromators, sample cell, detectors, and the recorders. And this is the picture of UV spectrophotometer. So we have a light source, and this is the collimating lens, and we have a parallel rays because this is kept exactly at the focus of the lens. And we have the next unit, what we call this is dispersing element. It can be a prism or a grating, so that we will have a specific wavelength that will pass through the sample. The sample absorbs the light, it can transmit or absorb, it can reflect, and the detector will detect the light and it is connected with a recorder, which is nothing but a readout. Working. The light source emits UV and or visible light, depending on the source. The monochromator isolates a specific wavelength of light. The isolated light passes through the sample and some of it is absorbed by the sample. The detector measures the amount of light that passes through the sample. This is nothing but transmitted light. The instrument then calculates the absorptions or transmittance of the sample at that specific wavelength. By scanning through a range of wavelengths, a spectrum is generated, which can be used to identify and quantify the components of the sample. A beam of radiation passes through the single cell. The reference cell is used to set the absorbance scale at 0 for the wavelength to be studied. It is then replaced by a sample cell to determine the absorptions of the sample at the wavelength. This was the earliest design. However, it is still used in both teaching and industrial labs. It requires a stabilized voltage supply to avoid resulting from changes in the beam intensity. Light sources. The following points are requirements. It should be stable, should not show fluctuation, it should provide light with sufficient intensity, it must be sufficient intensity for the transmitted energy to be detected at the end of the optical path, it should provide the UV and visible light needed for the experiment. Common sources include deuterium lamps for UV and tungsten or halogen lamps for visible light. Types of light source: hydrogen discharge lamp, deuterium lamp, tungsten halogen lamp, and xenon discharge lamp. Hydrogen discharge lamp. In hydrogen discharge lamp, pair of electrodes is enclosed in a glass tube filled with hydrogen gas. When current is passed through these electrodes, maintained at high voltage, discharge of electrons occurs, which excites hydrogen molecules, which in turn cause emission of UV radiation. It's a continuous source, covers a range 160 to 375 nanometer. And this is the picture of hydrogen discharge lamp. Deuterium lamp. It's similar to hydrogen discharge lamp, but instead of hydrogen gas, deuterium gas is filled. It provides the radiation with the range 185 to 370 nanometer. The spectroscopic technique is not useful below 200 nanometer since oxygen absorbs strongly at 185 nanometer. The region below 200 nanometers is called vacuum UV region. And this is the picture of deuterium lamp. Tungsten halogen lamp is a special class of lamps with iodine added to a normal filling gas. The envelope is made up of quartz to tolerate higher lamp operating temperatures. When a heat absorbing filter is inserted between the lamp and the sample holder to remove the IR radiation, the glass envelope absorbs strongly below 350 nanometer. The range of the wavelength is 350 to 3000 nanometer. The glass bulb enclosing the filament contains a low pressure of inert gas, usually argon. And this is the picture of tungsten halogen lamp. Xenon discharge lamp. In this, xenon gas is stored under pressure. The UV light produced by this lamp is of a greater intensity compared to hydrogen discharge lamp. Since the lamp operates at a high voltage, it becomes very hot during the operations and hence needs a thermal insulation. Emission of visible radiation also occurs along with the UV radiation. The range of wavelength is 200 to 100 nanometer. And this is the picture of xenon discharge lamp. Filter and monochromator dispersing element. A monochromator is a device which converts a polychromatic light to monochromatic light. It selects a specific wavelength or range of wavelengths of light to pass through the sample. This is often achieved using grating or prism. Types of monochromators. Prism monochromators. They are usually made up of glass, quartz or fused silica. Refractive type and reflective type. Grating monochromators. Gratings are made up of glass, quartz or alkyl halides like potassium bromide and sodium bromide. Back surface of grating is coated with aluminium to make them reflective. Two types of gratings, diffraction gratings and transmission gratings. Diffraction gratings. More refined dispersion of light is obtained by means of diffraction gratings. These consist of a large number of parallel lines, about 15,000 to 30,000 per inch, is ruled on highly polished surface of aluminium. To make the surface reflective, a deposit aluminum is made on the surfaces. In order to minimize to greater amounts of scattered radiation and appearance of unwanted radiation of other spectral order, the grating is blazed to concentrate the radiation into a single order. Transmission grating. It is similar to diffraction grating, but refraction takes place instead of reflection. Refraction produces reinforcement. This occurs when radiation is transmitted through grating reinforces with the partially refracted radiation. Filter. A filter is a device which allows only the light of required wavelength to pass through and absorbs the unwanted radiation. Types of filters are absorption filters, interference filters. So we have absorption filters. These filters have a bandwidth ranging from 30 to 250 micron. The absorption filter consists of a colored glass or a dye suspended in a gelatin and sandwiched between two glass plates. The colored glass filter has the advantage of greater stability. Each instrument is provided with a set of 12 filters to cover the range from 390 to 700 micrometer. A narrow spectral band can be obtained by coupling cut-off filter with other filter, but this combination decreases the intensity of light. Interference filter. Based on interference phenomenon at desired wavelength, thus permitting rejection of unwanted radiation by selective reflection and producing narrow band. It consists of a dielectric layer, CaF2, between two parallel silver films, which is sandwiched by glass plates. It has a band pass of 100 to 150 micrometer and peak transmittance of 40 to 60%. Sample cell. Sample cells are cuvettes are used to hold the sample solutions and they are placed in the path of light beam. So some of the pictures of cuvettes are shown here. So it's a rectangular cuvettes of different sizes. Some typical materials are optical glass 350 to 250 nanometer, special optical glass 350 to 2500 nanometer, quartz in the region infrared 220 to 3800 nanometer, and quartz far ultraviolet 170 to 2700 nanometer. The samples can be gases or liquids. The sample cell. It contains a solution of the substance which can be tested. It is usually very dilute with some solvent. The reference cell. It just contains a pure solvent. Sample measuring. If the light hits the transparent section, it will go straight through and pass through the cell containing the sample. It is then bounced by a mirror onto a second rotating disk. This disk is rotating such that when the light arrives from the first disk, it meets the mirrored section of the second disk that bounces it onto the detector. Reference measuring. If the original beam of a light from the slit hits the mirrored section of the first rotating disk, it is bounced down along the green path. After the mirror, it passes through a reference cell. Finally, the light gets to the second disk, which is rotating in such a way that it meets the transparent section. It goes straight through the detector. Detectors. Detectors are the devices which convert light energy into electrical signals that are displayed on the readout device. A sample absorbs a part of radiation and remaining is transmitted. The transmitted radiation falls on the detector, which determines the intensity of the radiation. The detector, like photomultiplier tube, measures the intensity of light transmitted through the sample. Types of photodetectors: photomultiplier tube, photovoltaic cell, and phototubes. Photomultiplier tube, it works on the principle of multiplication of photoelectrons by secondary emission of electrons. The emission of electrons is increased by a factor 4 or 5 due to secondary emission of electrons. So this is the picture of photomultiplier tube. A photomultiplier tube is a sensitive detector of light that converts photons into a measurable electrical current. So the output is current, the input is nothing but photons. It works by using the photoelectric effect to generate electrons from a photocathode, which are then amplified by a series of diodes. So diodes are sequentially kept with higher voltages, creating a measurable signal. Signal is nothing but a current. The next type is photovoltaic cell. When light rays falls on the selenium layer, electrons are generated and taken by the photocathode. Electrons get accumulated, which results in the generation of electric current. The current flow causes deflection in the galvanometer, which gives a measure of the intensity of the radiation. And this is the picture of photovoltaic cell. And the last one is phototubes. When light falls on the photocathode electrons, which travel towards the collector, anode, and generate current. The amount of current generated is directly proportional to the intensity of light. UV near IR spectroscopy is used to study the optical properties of photovoltaic cells, including their absorbance, reflectance, that are crucial for understanding and improving their efficiency and stability. Phototubes are widely used in UV visible spectrophotometers and other scientific instruments for detecting light intensity. And right side we can find out the picture of a phototube. Phototubes, also known as photoelectric cells, are devices that will convert light into an electric current. They typically consist of a vacuum tube, and this is a vacuum tube, or a gas-filled tube with a photocathode, that is light-sensitive surface, that emits electrons when struck by light. These emitted electrons are then accelerated towards the anode, creating a current. Detector and the computer. The detector converts the incoming light into the current. The higher the current, the greater the intensity of light. For each wavelength of light passing through the spectrometer, the intensity of light passing through the reference cell is measured. The intensity of the light passing through the sample cell is also measured for that wavelength. The spectrophotometer plots the absorptions of the sample across different wavelengths, creating a spectrum. Some of the key features. Single beam. Only one light beam is used to measure the sample and reference, as opposed to double beam spectrophotometers. Sequential measurement. The reference and the sample readings are taken sequentially. Simpler optics and design. This makes single beam spectrophotometers generally more compact, less expensive, and easier to maintain than double beam instruments. Wavelength range. Typically, it covers the UV-Vis range, that is 190 to 750 nanometer or 1100 nanometer. Applications. Commonly used for measuring absorbance, transmittance, concentration, purity, and characterizing chemical compounds. Advantages. Lower cost. Simpler design and construction lead to lower purchase and maintenance costs. Compact size. Easier to transport and store. Simpler operation. Fewer components and adjustments required. Disadvantages. Sequential, sequential measurement may be slower than double beam instruments. More susceptible to drift. Changes in light source intensity or detector sensitivity can affect the accuracy of measurements. May not be ideal for full band scanning. It requires more stable light source and detector for full band spectrum measurements.